Hey, welcome back. Today we're going to be talking about gravitation within a solid sphere and later a hollow sphere. And so this is primarily for AP Physics C mechanics students. And I've taken this from a FRQ in 1999. It's actually an important set of ideas to know because there used to be an entire unit on gravitation. Now it's not its own unit, but it's still important as a set of ideas to be able to understand how to think about gravity in different scenarios. So in this FRQ, there was some assumptions written into the question where we have a planet that has actually uniform density. And the planet is non-rotating, and there's a tunnel drilled through the diameter of the planet. So a bunch of unrealistic assumptions, but we're going to roll with it because the concepts in here are actually important and definitely worth thinking about, especially if you're an AP Physics C mechanics student getting ready for your test. And the question asks us to calculate the force on the ball at a distance little r less than big R from the center of the planet. Big R being the radius of the planet. Little r is the distance to an object that's actually within the solid sphere. So this is an object that is inside this tunnel, and we want to think about the force due to gravity on this object and what's going to happen. By the way, if we continue the problem past where we're going, it would go back and forth with simple harmonic motion. So there's lots of connections and lots of different problems that can be made for FRQs associated with these ideas. So it's definitely worth doing. All right, so only the mass inside the radius, little r, contributes to the gravitational force in the object. So that's the claim I'm making. In other words, all of this dark green mass out here in this outermost shell is irrelevant towards the force due to gravity on this little object right here. And the question is why? So I want you to think about that for a moment. And if you want to pause right now, go for it. But we are going to move on. Alright, so let me talk you through this. So again, the gravitational forces between the mass of the object and the nearly infinite amount of tiny little masses from the volume of the outermost shell cancel each other out. So let's think about why that is. Let's say this is the mass of our object right here. And if we continue with this, you could have a little mass here and a little mass here, and there's an attraction. But those attractions are all symmetric. Let's think about this dot here and this dot here. Again, they're symmetric, and they are opposing in direction. So what happens with that? Well, they're going to cancel each other out. It may seem like there's more forces as we go down here, and there would be, because we would assume that there would be more little pockets of mass all around here as we go around the shell, the outermost shell. That's true, but it's also true that those forces are lesser as you go down here. It's weaker and weaker because the distance involved is greater and greater. And these greater forces up here that you would have with closer masses near the top, it turns out that if you were to run this like as a simulation, all of the mass in the outermost shell cancels out in terms of the force due to gravity. So the mass in this outermost shell is actually irrelevant when considering the force due to gravity on this object in this tunnel. However, the force due to gravity between the mass of the object and all of the little points on the inside of this shell, you could say, this inner part of the planet, do not cancel out. And if you think about it, that does make sense because all of these forces have a general direction. So they can cancel each other out in the x-axis, so to speak. If we call this like y and this x, then you could say that in sort of the x-axis, I guess you could call it, they would cancel each other out for sure, but not in the y-axis. There's going to be a general force on the object going towards the center of the planet itself. So if you take a look at this, the net force is going to be towards the center of the planet. That's what we're saying right here. So the mass on the inside of the planet, all of that mass on the inside is relevant, but all of the mass on the outside is actually irrelevant when considering the force due to gravity on this object inside this planet. And that's a really important concept because you can do a lot of physics, a lot of interesting physics problems with those concepts. Alright, let's summarize here. The big idea is only the mass inside the radius of the object of interest contributes to the gravitational force on the object. Okay, so inside the planet, let's do some math associated with this. So inside the planet, let's think about what we have going on here and try to come up with the forces involved. So this is not on your equation sheet. It's just a basic definition of density, and it's something that you're assumed to know for an AP Physics C mechanics class. So please memorize this if you haven't already. Density is mass over volume. You probably had this as a middle school student. And let's think about what we know about this. If we assume a uniform density throughout, that definitely does simplify the problem quite a lot. Now we do know some things here. We do know we have this, let's label this the mass of the planet, but that's in a general sense. We're really interested in the mass inside the radius of the object as compared to the center of the planet. We also need to know what we're talking about in terms of volume. This is the volume of a sphere. That equation is actually on the backside of your equation sheet. So please remember to check the backside of your equation sheet for little geometry ideas, as well as importantly, some really crucial calculus ideas in case you just blank on the test or have trouble or something with the stress of the test itself. All right, so let's continue. So we do know more about what's going on the inside. If we want to think about the forces involved, this is where we're going with this. So you could say, okay, we have this. Now what we can do is let's isolate for the mass inside the radius of the object between where the object is located and the center of the planet. If we isolate for the mass of the inside, this is what we get. Now we can work with Newton's universal law of gravitation here. We do now know the mass inside the planet, and we can sub that into one of these masses. So let's go ahead and do that. And we're going to say this is the mass of the object, that's the mass that's left over. This is the mass in the inside of the planet. You sub in this equation that we had worked for into Newton's universal law of gravitation, and you start to see that some things happen here. We can continue to simplify, and we do end up with this equation here for the force due to gravity on this object inside this tunnel that goes through the planet. So this is really crucial here at this point. We have solved for this force due to gravity in this special case. And it's really important to notice that as little r increases inside the planet, Fg increases as well. So they are proportional to each other. So you could say the farther away the object is from the center of the planet, the greater the force due to gravity is, which makes sense. In a linear sense, this increases. And so to get at this, what we're going to be asked to do is to plot this as a graph. So we have come up with this equation, and we already know this equation as well, Newton's universal law of gravitation. And the question for part B is sketch the magnitude of the force F on the ball as a function of distance from the center of the planet. And here we have some values. So what we need to know is that as you approach the radius, the actual radius of the planet, that force is going to increase in a linear sense, right? Because as r goes up, so goes up Fg, you could say. So the beginning of this graph is going to look like this until we get to r, and then the second half of this is going to be an inverse squared relationship. As r continues to increase past the radius of the planet, the force due to gravity quickly drops off as an inverse squared relationship. So the second half of this graph should look something like this. Okay, and quickly, just to address a couple really crucial ideas that you should know about as well. So the question is, what would be the gravitational force inside a hollow spherical shell? So think about it for a moment. If you want to pause, go for it. Well, the answer is it's essentially zero, because the forces, again, are going to balance out to zero, very similar to the reasoning that we used previously for the outermost shell. That's going to be exactly the same concept that's applied here. Well, what about if we're talking about outside a hollow sphere? So if we have the object out here, what would be the gravitational force outside a hollow spherical shell? Essentially, the force due to gravity on this object. What do you think that would be? Well, in this case, what we're going to do is we're going to concentrate the mass at the center of this planet. Even though it's a hollow planet, you can think about the center of mass being in the center of this planet right here, and the force due to gravity of attraction between the object and the mass of the planet itself would play out exactly the same as if all of the mass was concentrated in the center of the planet here. So that's how you would go about solving that scenario. I do want to say I've done lessons on an entire year of physics, as well as most of the ideas in AP Physics E Mechanics. So if you have any questions down below, please let me know. And I hope you all have a great day. Take care.